Welcome, chemistry students. This is Chemistry Tales, and we are on Tale 16, Electrochemistry. We've already talked about redox reactions and understand how to balance those and predict which substance is undergoing oxidation and which substance is undergoing reduction. And so we're ready to move on to track 2, Electrochemical Cells. Let's begin by thinking about an electrochemical cell. First of all, we want to know what it is and why we are going to bother learning about it. So when you think about a redox reaction, okay, remember the fundamental aspect of a redox reaction is that one substance is going to donate electrons and the other is going to accept those electrons. So we have one substance A reacting with another substance B, and by definition, electrons are going to be given from A to B, resulting in A in an oxidized form and B in a reduced form. Okay, all right, so the critical thing here is we have movement of electrons. Okay, that's going to establish an electrical current. Okay, all right, so fundamentals. Redox reactions involve an exchange of electrons. Okay, when those electrons are exchanged, they set up an electrical current. Okay, all right, so let's do a unit analysis in important terms. Okay, electrical current, symbolized by I here, is measured in a unit of an ampere. An ampere is defined as the charge delivered per unit time. So it's coulombs divided by seconds, where coulomb is the charge. And a related parameter, which is going to be important and used extensively in later problems, is Faraday's constant, F, which is the charge on 1 mole of electrons. So that's going to have a value of 96,586 coulombs per mole of electrons. All right, so let's just tuck away that information and then come back. All righty, so current and electrical potential are related. And if you've had physics, you've looked at Ohm's law. Okay, V is electrical potential measured in volts, and I is our current, and R is resistance in ohms. Measured in units of ohms. Okay, but the important thing to recognize here is that volts and current are directly proportional. Okay, so volts is a measure of electrical potential. Okay, so this is one of our forms of energy that is involved with chemical processes. And a volt, unit-wise, is a joule divided by a coulomb. Okay, alrighty. So what is an electrochemical cell? Well, this is a device we're going to use to measure the electrical potential that occurs when the redox reaction happens. Okay, and another critical thing to know is if our redox process, here's the magical word, is spontaneous, okay, then we can derive useful electrical work, an electrical current, out of that redox reaction. Okay, this is the basis, forms the whole fundamental scientific basis of batteries that we use in absolutely everything. How far would you get in a day without a battery? You would have no cell phone, no calculator, no navigation, etc., etc. So this is really important chemistry that drives much of our society. So now we're ready to give consideration to what an electrochemical cell is and why we need it. So the cell is the apparatus that we use to measure the electrical potential of redox reactions. So there are different components in an electrochemical cell. On the right of this slide, you see a nice illustration of an electrochemical cell. Okay, within any cell there are 2 electrodes. Okay, and we have different names for the 2 electrodes. So if you'll remember, in a redox reaction we have 2 half reactions. There's an oxidation and there's a reduction. So those 2 half reactions happen they occur at these different electrodes. Okay, so the first electrode we want to give consideration to is called the anode. Okay, oxidation will always occur at the anode. Okay, the other electrode is the cathode. The reduction half reaction is always going to occur at the cathode. So I have a little convention of how I remember these things. I remember it by RC cola, and that tells me reduction happens at the cathode, oxidation at the anode, if you like to use those kind of acronyms to help you understand things. Okay, get rid of that for now. Okay, so in looking at the diagram, okay, the following will always be true. Okay, when you look at a diagram like this, the electrode on the left, this is the anode. This is where oxidation is going to occur. The electrode on the right is the cathode. This is where reduction is going to occur. Okay, all right, so in an electrochemical cell, oxidation happens on the left. So oxidation is where we give up electrons. So electrons are going to be given up at the anode. Okay, and they are going to traverse, they're going to move through the electrochemical cell over to the cathode, where the substance is going to take those electrons and be reduced. Okay, all right, so in the middle of the 2 electrodes we have a voltmeter. Okay, this is an instrument that's going to measure the electrical potential as those electrons move through it. So moving electron sets up a current, and remember from Ohm's law, voltage equals current times resistance. So that current is going to create an electrical potential, a voltage, that gets measured by the voltmeter. Okay, in considering a circuit like this, we have the movement of negative charge. The anode, as you'll see here, is considered the negative electrode because it's the source of the negative charge, and the cathode is considered the positive electrode. Okay, so we have moving charge that we always have to have a balance. So if negative charge is leaving the anode and entering the cathode, we have to counteract that. So to complete the circuit of the apparatus, we have what is known as a salt bridge. Okay, that's this component right here in the diagram. What a salt bridge is, it connects the 2 electrodes. Okay, it contains a gel in which we have an ionic substance, and those ions can move within the gel. Okay, so with our illustration here, we have potassium chloride in our salt bridge. If you'll remember, that's a soluble ionic substance, so we have potassium ions and chloride ions. Okay, So they're going to help counteract this moving negative charge. So if you think about it, we've got these electrons originating from the anode. So the negative charge is leaving the anode. So that means the chloride ion in the salt bridge is going to move in this direction to replace that negative charge. Because we are introducing more negative charge into the cathode, we have to counteract that. So the potassium ion in the salt bridge is going to migrate towards the cathode. So the salt bridge, once again, it completes the circuit, the electrical circuit, and it counters the movement of the negative charge out of the anode into the cathode. Okay, one other thing you see in our diagram is this, what we call a shorthand notation for our electrochemical cell. Okay, so that shorthand notation equates to the diagram above. It tells us everything we need to know about what's in the electrochemical cell. Okay, so let's look at the actual reaction that I'm showing in this illustration. Okay, we have copper sulfate reacting with zinc metal to provide zinc sulfate and copper solid. So this is a redox process. So let's go in and assign oxidation numbers, break it up into the two half reactions, and have a better understanding of how this electrochemical cell works. Okay, so copper sulfate, starting here with this reactant, that's a soluble ionic substance. So you actually have copper 2+ ions in solution, sulfate 2- ions in solution. That's reacting with zinc metal, producing zinc sulfate, once again a soluble salt. So that's zinc 2+ ions, sulfate 2- ions, and as a product we have copper metal. All right, so if we go in and assign oxidation numbers, applying all of our rules, copper is a monatomic ion. I'm going to get rid of some of this annotation up here so we got room here. Okay, copper is a monatomic ion. The charge on the ion is +2, so the copper is in a +2 oxidation state. That's the oxidation number. Okay, we have the sulfate anion here, but notice nothing's happening to the sulfate anion. So it's kind of a spectator ion. You could go in and assign oxidation numbers, but there's no sense because it's not changing oxidation state. Zinc, that's a neutral element. Oxidation number is 0. And as products, we have zinc +2 ions, so that's +2 oxidation state. And the copper is copper metal, so that's oxidation number 0. So in looking at this reaction, we want to break it up into the two half reactions. So the substance that is increasing oxidation number is losing electrons. That's oxidation. So notice that the zinc is going from 0 to +2. That's an increase in oxidation number. So the half reaction happening at the anode is oxidation. So this is zinc metal yielding zinc ions in solution. Okay, and to balance my half reaction, since I have a +2 charge on the right, I must add 2 electrons. So there's the half reaction happening at the anode. At the cathode, okay, notice your copper is going from a +2 oxidation state to 0. So for the reduction occurring at the cathode, we have copper ions yielding copper metal On the right, the copper metal is neutral. Since I have 2 positive charges on the left, I must add 2 electrons. So there's your reduction. Okay, so within the electrochemical cell, we always have, you've got your solid metals, right? The zinc at the anode, the copper at the cathode. So in the illustration here, notice you've got a zinc terminal, what we call a terminal. Okay, a terminal is simply metal, which is a good conductor of electricity. Okay, so that metal is going to allow the electrons to move over through the device over to the cathode. Okay, and in the cathode, you know, you've got copper metal as your terminal. All right. So those are the components within the electrochemical cell, and coming down to our shorthand notation, okay, what you will always see in a representation of an electrochemical cell is the following. All right, we have the terminal of the anode, which is your zinc metal. Okay, the vertical lines represent phase boundaries. So we're going from a solid, and then surrounding this solid, we have a solution. There's a solution of zinc sulfate. That's the source of your zinc ions. Okay, so we'll do it this way. So you've got terminal, you've got a phase boundary, because we're going from solid to solution. Now you've got your solution. Technically, I should convey the concentration of my solution. So you oftentimes will see this as like 1 molar aqueous. Okay, all right. And then this double line over here separates over here. This was our anode, and on the right is our cathode. And the separation here is your salt bridge. That double vertical line represents the salt bridge. Okay, so on the right, your cathode is comprised of your terminal, the copper metal. There's a phase boundary, and then the solution, the copper sulfate, and technically, once again, you should convey the concentration of that solution. Okay, so that's the shorthand notation that tells you everything that's in the electrochemical cell, and you should be able to write a redox reaction. If you look at just the shorthand notation of an electrochemical cell like this, you know that this is the anode, this is where oxidation is occurring, and you know this is the cathode, and this is where reduction is occurring. The next thing we want to think about when we look at our electrochemical cell is the significance of when we measure the cell potential, what the sign on that cell potential tells us. Okay, so 2 possibilities, obviously. If the cell potential you measure is positive, okay, what that tells us is that the process occurring in the cell is spontaneous. Okay, electrons will just spontaneously be generated at the anode, flow through the voltmeter, and go over to the cathode. Okay, and the redox process will just spontaneously happen. Okay, so that's what a positive cell potential tells you. When an electrochemical cell behaves in this manner, we call it a voltaic cell. We also refer to it as a galvanic cell. Okay, important thing about redox processes that have a positive cell potential, we can derive useful work, electrical work, out of those cells. Okay, and this means that a current, an electrical current is generated. So these are the kinds of cells that we use as batteries. Okay, think about how important batteries are to your day-to-day life. Your cell phone, any kind of digital device, typically has its own power source to operate it. And so batteries basically rule our life. So they're very fundamental and important aspects of our modern society. All right, so the opposite scenario is for the cell potential to be negative. Okay, so what does that tell us about a redox process? Well, it is non-spontaneous. If you want this redox process to happen, okay, you are going to have to put into the electrochemical cell an external power source. Or, in other words, an external battery to drive this process to happen. Okay, so the next important thing we want to be able to do for a redox process is to predict what the cell potential is going to be. And in order to do that, through years of research, chemists have come up with data tables of a property known as a standard reduction potential for any half reaction. Okay, and in that set of data, okay, we can simply look up values for the two half reactions happening. Okay, there's the half reaction at the anode and the half reaction at the cathode. So I just simply need to look up values for the standard reduction potential happening at the cathode, and I need to look up a value for the standard reduction potential happening at the anode. Okay, now keep in mind the process happening here is oxidation, so when you look up the value for this half reaction, you have to flip it and make it a reduction. Okay, all right, so the overall cell potential for any redox process can be predicted, okay, using this equation. And we simply take the standard reduction potential of this process, enter that value here, and we look up the standard reduction potential for the flip of the process happening at the anode, and we plug in that value there, and that allows us to calculate the cell potential. Notice that all of these values, we have the little superscripts up here. So these are measurements made under standard conditions. Okay, so once again, temperature is 25 degrees C. Any solutions, our concentrations are technically 1 activity unit, which is approximately 1 molar. And if we have any gases involved, the pressure of any gases is 1 bar. In this slide, we look at the standard reduction potential data tables. So, very conveniently, we can go to these data tables and look up the reduction potential for any half reaction. So you will see over here on the left are the potential values, and over here on the right are the half reactions. Okay, so where this data comes from, chemists actually create an electrochemical cell as the one shown here. Okay, at the cathode, we are going to have 2 hydrogen ions gaining 2 electrons, forming H2 gas. That electrode is known as a standard hydrogen electrode. It's what we call a reference electrode. Okay, and so we are going to measure the electrical potential that exists between that electrode and desired half reactions at the anode. Okay, so in this case, zinc is being oxidized to zinc plus 2 and 2 electrons. The electrochemical cell records a value of 0.76 volts. Okay, we are going to define the cell potential of the standard hydrogen electrode. This is by definition going to be 0, so this is at the cathode. Okay, all right, so that tells us that this zinc half reaction, okay, since the oxidation is recording a positive 7.76 volts, the reduction would be a negative 0.76 volts. Okay, so that's how all these data are compiled. We put our desired half reaction materials at the anode, and we measure those values, and then we flip the sign because we're not actually doing oxidation. We want to list these as a reduction. Okay, so just important things to keep in mind. You know, oxidation and reduction are complementary processes, and so the cell potentials are equal in magnitude, opposite in sign. So when you look at this data table, these are literally reduction potentials. Okay, so if the actual process is happening as an oxidation, you need to flip the sign. Okay, another important thing that this data table does for us, okay, the one that we're looking at is compiled with the most positive standard reduction potentials at the top, the most negative at the bottom. Okay, so what that tells us is the half reactions that have very positive values. Remember, the more positive something is, the more spontaneous it is. Okay, so these reductions up here occur readily. Okay, the more positive the value, the more favored is that reaction. So these substances up here, these are your strongest oxidizing agents. Remember, oxidizing agents take electrons. They get reduced. So as you move down these half reactions and you look at the different substances, we are decreasing strength as an oxidizing agent. Okay, so these are your strongest oxidizing agents. These are your weakest. And then we can consider the opposite. Okay, if you want to look at species that are your best reducing agents, they're best at giving up electrons, those are going to be the ones that have the most negative reduction potential. So down here at the bottom, okay, these substances are those that most readily give up electrons. So these are your strongest reducing agents. Okay, so and look at what they are. Metals and metals in the upper left-hand corner, basically. Alrighty, as you move this direction and you're looking at these substances, okay, you are decreasing strength as a reducing agent. Okay, so as those values, as the reduction values get more positive, you're reducing the strength as a reducing agent. Okay, so those are the important takeaways from this slide. Okay, when using data tables of standard reduction potentials, remember oxidation and reduction are opposite sign. And the more positive the standard reduction potential, the greater the strength as an oxidizing agent. The more positive the value of the reduction potential, the greater the strength as a reducing agent. With this slide, we want to go back and predict the overall cell potential under standard conditions for the redox reaction of the cell we were giving consideration to. So let's remind ourselves the two processes happening at the two electrodes. So at the anode, we have oxidation occurring. That was zinc metal yielding zinc ions and 2 electrons. At the cathode, reduction was occurring, and we had copper ions gaining 2 electrons, being reduced to copper metal. Okay, so when we want to calculate an overall cell potential, we go to our data table and we look up, let me use a different color here. I'm going to get rid of that for a second. We look up the standard reduction potential for the half reaction at the anode. Okay, and remember in the data table, I'm looking for the inverse. I'm looking for the reduction. So I'm looking for zinc 2+ ions gaining 2 electrons. Okay, so where is that? So in the data table, here is zinc 2+ gaining 2 electrons going to zinc metal. That standard reduction potential value is a negative 0.76 volts. Okay, now I do the same for the half reaction at the cathode. I look up the standard reduction potential for the half reaction at the cathode. So this one is a reduction, so I look exactly for copper 2+ gaining 2 electrons going to copper metal. That half reaction is right here in my table, and the standard reduction potential is a positive 0.34 volts. So now I'm simply going to plug these values into my equation up above. My cell potential looks like that. So my overall cell potential under standard conditions is, okay, the reduction potential for the half reaction at the cathode, that is a positive 0.34 volts, okay, minus the value I looked directly up in the data table for the half reaction at the anode. That is directly from the data table, a negative 0.76 volts. Once again, notice this negative sign takes into account the fact that the half reaction at the anode is actually oxidation. Okay, All right, so that leaves us with an overall cell potential of plus 0.34 volts plus 0.76 volts. This is a positive 1.10 volts for that redox reaction in that electrochemical cell. So we can now predict the kind of cell that this is because it's positive. This half reaction, or this reaction, is spontaneous. Electrons spontaneously flow from the anode to the cathode. This is a galvanic cell, also known as a voltaic cell. And it generates an electrical current. So you could potentially use this as a battery, a power source. So with this slide, we just want to give some consideration to the importance of the electrochemical cells in our lives and how frequently we utilize batteries, which are your electrochemical cells in which the cell potential is positive. We use those as a current source to power many of our devices. And then the opposite kind of cell is an electrolytic cell in which we actually provide a power source to drive a redox reaction for different reasons. A lot of industrial processes generate desired products using electrolytic cells. So let's just go over some of the most common ones that we encounter. So in terms of the galvanic cells, voltaic cells, okay, those are those for which the cell potential is positive. These are your batteries. Okay, all right, so let's look at one example that should be very common to you, a lead storage battery. Okay, and where do you find a lead storage battery? Oh, that would be in your car. Okay, so typically, you know, you go to buy a battery for your car. These are 12-volt batteries. So what is actually happening in those components? Well, here you go. So the negative electrode, that's your anode. Okay, the half reaction happening here is lead yielding lead ions and 2 electrons. Those lead ions are in the presence of sulfate ions, so you've got lead sulfate. Okay, there's the potential for that half reaction. Okay, and then your cathode, the positive electrode, is here. Okay, you have lead oxide reacting in acidic solution, hydrogen ions, gaining 2 electrons, going to lead plus 2 ions in water, okay, also in the presence of the sulfate ion. And there's your cell potential for that half reaction. So the overall redox reaction happening in the battery in your car is right here. So you've got lead reacting with lead oxide, and notice that's sulfuric acid, so acid battery. That's why you've got acid in your battery. And there's your overall redox reaction. So this is one cell in your battery generating a positive 2 volts approximately. And in any car battery, you typically have 6 cells. So that's where we get the 12-volt battery. All right, and there's a number of other types of batteries we use for different applications. Okay, examples include the fuel cell used on the space shuttle. Okay, potential energy source here. So we actually take reaction of hydrogen gas and oxygen to produce water. Okay, and so that is the power source used on the space shuttle. Other important things, a lithium iodide battery. Okay, this one, okay, your performance characteristics have to fit the function of what you're going to use that for. This is used in pacemakers in your heart. Okay, heart patients that have conditions such that occasionally the heart needs to be stimulated with an electrical current to make it continue. So what might there be desirable characteristics for this kind of battery? Well, you probably don't want to replace it too often. So one of the characteristics of this battery is it lasts 10 years. Okay, it's very reliable. It has high resistance, low current, etc. So different batteries have to be designed for different functions. In your calculator, typically a nickel cadmium battery. Okay, also used for power tools, that kind of thing. So we are surrounded by batteries in our day-to-day life, and the chemistry involved is very important. So not everything in terms of redox reactions generates a current. Other processes are those in which the cell potential is negative. Those are your electrolytic cells. Chemical industry uses these kinds of reactions to drive desirable processes, generating desirable products, such as a down cell. This is used to produce sodium and chlorine. So your products of the down cell, sodium and chlorine gas. Okay, you have to use an external power source to generate that. And basically the two half reactions for that are sodium ions gaining an electron, forming sodium liquid, and chloride ions yielding chloride molecules, gaseous phase. So this is your oxidation, this is your reduction, and these products are the consequence of that redox process. Okay, so there's all kinds of different industrial applications of electrolytic processes that we use. Electroplating happens where we reduce metals, such as if I want to place zinc metal on a surface of a species, I would simply provide a current source to make that process happen and deposit this metal on a surface. So here's zinc deposited on a surface. So electroplating is an important electrolytic process that is used quite a bit in industry. So those are some good examples of applications of electrochemical cells that are prevalent in our day-to-day life. And the next section we're going to look at is the relationship of the cell potential on spontaneity. And if you recall from our previous chapter, the ultimate parameter that dictates spontaneity is Gibbs free energy change. See you soon.